Noah, are you going to make a move? It's been your turn for like 15 minutes now.
Man, I should not have sacrificed my bishops, rooks, and queen like that. It seemed like a good idea, but now I have no idea what to do with all these pawns and my two horsies.
Well, keep thinking about it, amigo. I'm going to go get the Prechos out of the oven.
Maybe I can sneak this pawn up the outside and get him into the end zone.
I'll get that.
Pete?
Hey, Noah.
You just walked into the. Oh, hey! It's Pete from the future again. What are you here to warn us about this time, Pete? Is the show okay?
Oh, the show's fine, but I'm not Pete from the future. I'm from right now.
So how'd you get from the kitchen to outside the front door?
Well, I'm from right now, but I'm not from right here. I come from a parallel universe.
Whoa. We get the coolest visitors here at the math club. What are you doing here?
I happen to know that you guys were about to do an episode about multiple dimensions and thought you might want a co-host who comes from another dimension.
That's an awesome idea. One small problem, though. It might be kind of hard for the audience to tell the difference between our Pete and you. You sound pretty much exactly the same.
Oh, they won't have to. We're going to send your Pete to my dimension to do the show with my Noah. Over there, he'll be the guest host from another universe.
Nice.
I thought you'd like that.
So, how many other dimensions are there?
Well, first of all, let's be clear. We're going to talk about spatial dimensions, not parallel universes. And most people would probably answer that there are three. But in fact, there are a whole lot more.
How many more?
Do you remember our episode that opened at Hilbert's Hotel?
Yeah, that was our episode about infinity. Are you trying to say that there are an infinite number of spatial dimensions?
Tell you what, why don't we get your Pete off to my dimension, and then you and I can talk about it.
Do you think the other Pete and I can finish our chess game first?
To tell you the truth, in my universe, we already finished it. And it's probably in your best interest to just concede right now and save what little dignity you have left.
It was that bad, huh?
Oh, it was much worse. My Noah whined for over an hour afterwards about the Great Horsey Massacre of 2024.
Yeah, that sounds like me. Okay, let's hop to it. By the way, what should I call you?
How about Pete?
Pete. 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 Yeah, I like it. Pete it is.
All my two-dimensional boundaries were gone. I had lost to them badly.
Hey, Noah, we're back at the math club. How's it going? What have you been up to?
Hey, Pete. It's great to be back here. It's been a little while for us. I have been super busy at work. As you know, I'm a teacher on special assignment for my school district. And I had two huge events that I was in charge of that both happened between our last episode and this one. One was the district-wide science fair, and the other was a really cool middle school math competition called Math Counts. Have you ever heard of that?
I haven't, but now I definitely want to.
Yeah, it was really cool. Each school sent kids, and the kids competed in rounds both individually and as teams. And at the end of the day, the top 10 students at each grade level and the top team at each grade level was announced. It was super exciting and really fun. In fact, I was so impressed that I think we might want to do an episode on the Math Counts program at some point.
Oh, yeah, totally. I think that's a great idea.
So, what have you been up to since our last episode?
Well, I just finished watching The Queen's Gambit, which is a fantastic series on Netflix. It's about chess, it's set in the 60s, and it's just super cool. And aside from that, I've been spending a lot of time thinking about the three-dimensional sphere.
The three-dimensional sphere? Can't you just say the sphere? I mean, aren't all spheres three-dimensional?
Oh, definitely not. Probably what you mean by the sphere is only two-dimensional. So the ordinary sphere is two-dimensional, and I've been thinking about its three-dimensional big brother, actually, which is called the three-dimensional sphere.
Wait a second. What do you mean the ordinary sphere is two-dimensional? If that were true, then how come when I was teaching third grade and I bought a set of manipulatives called three-dimensional solids, the sphere was one of them?
Well, actually, that wasn't the sphere. That was a solid sphere, which we normally refer to either as a ball or a disk. So it is, in fact, three-dimensional because it's got this solid inside, which then is bounded by the infinitely thin ordinary two-dimensional sphere on the outside.
So this infinitely thin two-dimensional sphere, that's like what? Like a soap bubble, kind of?
Tiny bubble.
Yeah, actually, a soap bubble is a really great way to think about it. The sphere is hollow on the inside, the same way the circle is empty on its inside. It is something we would draw on the XY plane, but it only includes that infinitely thin curved line, if you will, that infinitely thin curve, and nothing on the inside.
All right. Well, I hear all the words that you're saying, but it just doesn't add up in my mind because a sphere is clearly three-dimensional. We live in a three-dimensional universe. I can hold the sphere in my three-dimensional hand and I can see that it's got length and it's got width and it's got height. I can move along it in any of those directions. So how in the world is it two-dimensional?
Okay, those are great questions. Let's just take a step back, take a deep breath, and ask, what could it possibly mean to say that the sphere is two-dimensional? And I'd like to explain this by using an analogy. Okay. So here you and I are at various places on the surface of the earth. I'm in my home, which is in Washington State. You're down there in California. And both of our locations can be identified with a latitude and a longitude.
Well, that's true. I guess when you look at it that way, you only need two numbers, the latitude and the longitude, to identify any particular spot on the globe.
Yeah, that's right. Latitude and longitude, just a pair of coordinates, is enough to get you anywhere on the surface of the earth. For example, Seattle, the closest big city to me, is located at a latitude of 47.6 degrees north and 122.3 degrees west. And San Francisco, the closest big city to you, is at 37.8 degrees north and 122.4 degrees west. So with just two coordinates, we're able to specify exactly where those two cities are.
Well, that makes sense. And I think I see what you mean now. When you look at a map of the Earth, there's a latitude-longitude grid that's very similar to the XY coordinate grid. And a map clearly is two-dimensional, so I guess the surface of the Earth that it represents must be too. Just like on the XY coordinate plane, we can specify any location on the surface of the Earth with just two coordinates. And in that way, Earth is just like an ordinary sphere.
Yeah. And it's kind of interesting that you mentioned a flat map because, in fact, the Earth is so large compared to us humans that when we look around us, it might appear that the Earth is flat. I mean, you can't necessarily tell that it's going to curve around in all of these circular directions. And some people seem to be convinced that maybe the Earth actually is flat and it's not round.
Yeah, there's a certain society I'm thinking of that is pretty adamant on that point.
So if we think of a sphere, then the same way we would think of the surface of the Earth, and I just mean the surface now. I don't mean digging down, looking for dinosaurs into the soil and the tectonic plates and the lava.
Liquid hot magma.
That's not part of the surface. Just the surface is a model for what we mean by a sphere, which brings us back to your initial metaphor of a soap bubble. Really, that is the perfect way to think about what the ordinary two-dimensional sphere is. And what I've been thinking about is a sphere that has one additional dimension to it.
So is the sphere that you're thinking about more like the one that came in my manipulatives kit of three-dimensional solids? It's a filled in sphere that's not hollow?
No. So this three-dimensional sphere naturally lives in a four-dimensional space. And what it encloses on its interior is a solid chunk of four-dimensional space. So it's hollow on the inside, but it's hollow in a way that has more dimensions than our apparent world that we live in.
Okay, hold on. Back up a minute. Now we're getting into four dimensions. I was a little confused when we were talking about two, but I at least could get my mind around two dimensions. I can get my mind around three dimensions, but what in the world are we talking about when we say something has four dimensions? I know I've heard it said on occasion that time is the fourth dimension. Is that what you're talking about?
No, although there is a four-dimensional system known as space-time that physicists think about all the time, and it does include a fourth coordinate that represents time in addition to the three spatial coordinates. But what I'm thinking of really at a basic level is just four different coordinates bundled together in parentheses. So like X, Y, Z, and W. I've got four different real number coordinates, and I'm imagining a space in which all four of those coordinates can freely move around in whatever fashion they would like.
Okay, but I can't really picture in my mind's eye what we're talking about with this fourth dimension. Is there some way you can describe this so we can picture what this looks like?
Well, in some ways, I think this is the power of math, that it allows us a way to enter spaces that are otherwise difficult or impossible for us to envision. So there are tricks and devices and analogies and comparisons that we can make to try to quote unquote picture the fourth spatial dimension. But really, I kind of want to turn that inside out and say, no, our eyes aren't equipped to directly picture four spatial dimensions. That's why we send the math in for us. The math is like a probe that can travel into these spaces that we otherwise cannot access. And if those spaces happen to have a fourth or a fifth or a sixth or some other number of coordinate dimensions, fine. We will let the math be our eyes, and then we will interpret the results mathematically, intellectually, when our probe comes back from its journey and reports back to us.
I love what you're saying about sending the math in for us. Like the math kind of goes in where it's impossible or deadly for people to go and does the work that we can't do without it. But at the same time, I'm still having a hard time understanding what we mean when we say, just add an extra spatial dimension, just add a fourth dimension. I still don't quite get what that even means. What does it mean to say something has fourth dimensionality as opposed to three dimensionality?
Right. I think there are a couple of things that we can do to help us here. So, first of all, somehow going from three coordinate dimensions into a fourth, adding a fourth one, that puts us at some kind of perceptual boundary. Like it's difficult to go across that. So, let's use a tried and true technique and reduce the number of dimensions that we're working with. If I give you two coordinate dimensions, X and Y, you could picture them in a pair of parentheses separated by a comma. And now I want to say, let's add a third one. What is that experience like for you?
Well, if I just have two spatial dimensions, X and Y, I can kind of graph that on a piece of graph paper. I go over so many units on the X axis, and then I go up so many units on the Y axis, and I end up at, let's say, spot 5, 3. If we want to add a Z axis, that's going to take us off the paper. The Z axis is going to run perpendicularly to the plane that the other two axes make, and it's going to come up above the paper so that I can put a point at, let's say, 5, 3, 11, which should be 11 units up and off the paper. I understand that. And I think I understand that because we live in a three-dimensional world. So I can picture exactly what adding that third dimension adds. But I can't picture now what adding a fourth dimension would look like because I don't live in a fourth dimensional world. So that's where I'm getting stuck.
Well, put yourself in this mindset. Have you ever seen the comic strip XKCD?
Oh, yeah. All the characters are drawn as little stick figures.
Right. And if you picture a stick figure living down in that plane that you just drew, that little guy can move around, say, 5 units to the right and 3 units up, and very happily inhabit this X and Y plane. But when you say, now I'm going to go up 11 units in the Z direction, in this third mutually perpendicular direction, XKCD guy can't go with you, right? And because you are leaving the plane in which our little stick figure lives. That's what would have to happen here in our three-dimensional space. If something were to move now in a fourth dimension, it would appear that it simply disappeared. If you and I were hanging out and I said, I got to go into the fourth dimension, see you later, I would literally just disappear in an instant because now I'm moving on a new coordinate direction that is not available to you.
Mr. Murgatroyd! He vanished into skinny air. Disappeared even.
I see what you mean. You know what this reminds me of? About a year ago, I was reading a book called Quantum Void. It was part of the Quantum series by Douglas Phillips. And in this book, kind of a side point was that somebody invented this cap to put on top of factory smokestacks. And it was basically an elbow shaped joint. But instead of bending 90 degrees in any of the three dimensions we know of, it bent 90 degrees into the fourth dimension so that pollution could come up and out the smokestack, go into one end of this tube, and then just disappear like you're describing. Of course, it led to all kinds of trouble down the road. But I think that's the same sort of idea of what you're talking about, of something just disappearing because we can't see things moving in that dimension.
Yeah. In fact, this reminds me of another piece of literature that is very famous for its explanation of dimensionality, and that is Flatland, written by Edwin A. Abbott. The story of Flatland takes place essentially in an XY plane, and the inhabitants of Flatland are polygons with different number of sides, and they move around just as we described our cartoon stick figure moving around in the world of XKCD.
Oh, yeah. Now that you're describing this, I think I remember reading this book back in college. Was there some aspect to it that the more sides a polygon had, the higher its social status was, or something like that?
That's right. And I think if I'm remembering right, the queen is actually a circle, which is sort of the limiting case of a polygon with infinitely many sides, in quotes, because that's not actually a thing. But yeah, that's exactly right. So the queen is a circle. And in that world, the inhabitants of Flatland would have a very difficult time imagining the two-dimensional sphere, which if you worship a circle, the sphere would somehow seem extra special because it's equally curvy and round, but it's got an extra dimension to it. So it would be pretty cool if you lived in Flatland and you could somehow encounter the sphere, right?
Oh, yeah. And they did encounter the sphere, didn't they? Because as the sphere passes through or intersects the flat plane of Flatland, you kind of get a cross section of it at any given time. And the sphere is going to look like circles of varying sizes, depending on what part of it is intersecting that plane, right?
Yeah. When the sphere first makes contact with the plane of Flatland, it's just a single point. And it's as if that point just materializes out of thin air. And continuing to pass through the plane, the sphere would appear as concentric circles that are getting larger and larger until the sphere reaches its equator. And then as it continues its journey, those circles would begin to shrink smaller and smaller until they collapse to just a single point, and boom, it disappears and it's gone.
So the special property that the sphere would appear to have to a resident of Flatland is it would look like a circle, but a circle that had the power to alter its diameter, to make its diameter bigger or smaller at will.
Exactly. And we can ask, Well, what would happen if the three-dimensional sphere tried to pass through our world? What would we see?
Well, I would guess we would see what looks like a soap bubble sphere, right? We would see just that part of it in our three-dimensional world. If the residents of Flatland would only see the circle, then kicking it up one dimensional notch, we would see the sphere, the two-dimensional sphere.
That's right. We would initially see a single point of contact, and then from that point of contact would balloon out a sequence of two-dimensional spheres that grew larger and larger until they reached some maximal diameter. That's when the equator of the three-dimensional sphere is passing through our three-dimensional world. And then that sphere would appear to shrink smaller and smaller until it becomes a point and then vanishes. And so we can reason analogously in lower dimensions about what happens in higher dimensions.
That is really cool, Pete. And I got to hand it to you. You just described that in a way that I feel like I get it. I can picture it now. I wasn't sure what we meant before about a four-dimensional object interacting with a three-dimensional world, but using that analogy from Flatland really helped me to visualize it. So thank you.
Well, you're welcome. And I can't claim, I mean, I learned this myself from various places, including Flatland. And so, I can't claim to be the originator of it, but it's such a profoundly useful analogy that it has stuck with me ever since I first learned it.
Yeah. So now getting back to my original question that I asked at the very beginning of the episode, now that I sort of understand what we mean when we say add a dimension, how many times can you add a dimension? How many spatial dimensions are there?
Yeah. Once you allow yourself to let go of, well, how do I picture that new coordinate in my three-dimensional world? Right. As soon as you can kind of let go of that, you realize there's no limit. You want a fifth dimension? Great. X, Y, Z, W, T. Oh, you want another one after that? Fine. Call it U. Now you need an 11 dimensional space. Fine. I can write down 11 coordinates and think of them as a bundle representing a single geometric point in some larger dimensional space.
All right. So, Pete, you just explained to us that there is a three-dimensional sphere sitting within a four-dimensional space. Does this mean that there's also a four-dimensional sphere sitting within a five-dimensional space and a five-dimensional sphere sitting within a six-dimensional space and on and on and on forever and ever?
That's exactly what it means. And what you are shining a light on here is that in any given dimension, we have some space, and inside it, we have a sphere whose dimension is one less than the ambient space in which it lives. And that relationship persists through all of the dimensions as they march up to infinity.
So you just mentioned the ambient space in which it lives. So that would be like, for example, in our universe, the ambient space is three-dimensional, but in some theoretical mathematics, the ambient space can be four-dimensional, five-dimensional, 10-dimensional, 100-dimensional, et cetera.
Yeah, exactly. And so this soap bubble that you introduced to us several minutes ago is an excellent model of a two-dimensional sphere. And it lives in our three-dimensional world, which is the ambient space that contains that two-dimensional sphere. And there's something very natural about this dimension comparison. The sphere has dimension 2. It lives in an ambient space of dimension 3, which is one higher. And any kind of geometric surface that has that dimensional relationship with its ambient space is called a hypersurface. And so a sphere in our world is a hypersurface in three-dimensional space. And the three-dimensional sphere is a hypersurface in four-dimensional space. And the four-dimensional sphere would be a hypersurface inside five-dimensional space.
There is a fifth dimension, beyond that which is known to man. It is a dimension as vast as space and as timeless as infinity.
That's really intriguing, but I want to bring it back to the real world for a minute, because as you know, I'm rooted right here in three-dimensional space. As intriguing as all of this is, how does it apply to anything in the real three-dimensional world? How is this math useful considering that there really only are three spatial dimensions in our universe?
Well, I think there are a number of responses to that question, but here's perhaps the simplest and most direct. How do you know that we don't live in a three-dimensional sphere?
Well, when I bought my house, they didn't mention anything about that on the literature, and I think they would have had to have said something.
Okay, wise guy. What I'm getting at is we don't actually know what the large scale geometric shape of the universe is. And for all we know, we could be living in a three-dimensional sphere. That could be the geometry of the universe. Beyond that, if you look into various formulations of string theory, the universe is thought in those theories to be either 10 or 11 dimensional. And so, if you're not equipped to understand and study and analyze spaces that have 10 or 11 dimensions, then you can't study the universe. Might as well close down shop because you're stuck at 3 dimensions. So, I think that's one practical way to answer the question.
And I think you kind of just blew my mind with your how do you know we don't live in a universe with more dimensions and we just are living in a three-dimensional pocket of it. I think that was a really cool idea that I need to give some thought to after we're done recording this episode.
Well, you probably, like most of us, imagine that we live in a three-dimensional space that appears, at least when I look around me, to have, oh yeah, there's an X and a Y and a Z coordinate direction. If I look in the corner of any one of my rooms, I can see, oh yeah, I could, there they are. The ceiling has an X and a Y, and the walls come up in a Z direction. And there's there's right angles sitting in the corner. I'm in a three-dimensional Euclidean space where I got straight lines going off in every direction, and that makes sense. Well, we mentioned earlier that the Earth looks flat locally. Like you got to have some vantage point to understand that globally it's curved. Well, maybe that's true of the universe. Maybe globally it's curved. It just looks to us like, oh, it's got three flat dimensions, not curved.
That is a really, really great analogy and a really great question. I love it.
And there's another way that one could respond to your question about bring it back to the real world for us. How is it useful? Do you remember our conversation with Dan Finkel from Math for Love?
Yeah, sure.
Well, we spent a lot of time talking with him about mathematics as a place of play, as a place of usefulness, as a place of history and storytelling, and so much more than simply what is it good for, that I would reflect that very same point of view back at the question of why are these dimensions useful? They are, but that's telling only a small part of the story. There's so much more beyond the immediate applicability of this dimensional thinking. Even if we can't imagine the usefulness of it, we have to be careful and just sit with it for a while because some new doors will open for us for sure.
Yeah, I get what you mean. Well, Pete, this has been a really entertaining conversation about dimensions. I think we would be selfish if we didn't get you back to your own dimension soon and get our Pete back here. I'd like to compare notes with him to see how their episode went over in your home dimension.
Alrighty.
So thanks for being our special interdimensional guest on today's episode, Pete. And Math Club, if you have anything you'd like to share with us about multiple dimensionality or any other math topics, please feel free to reach out to us either on email, Twitter, or through our SpeakPipe account. You can find links on how to reach us on those platforms in our show notes.
Thanks for listening, Math Club. We will catch up with you in our next episode.
See you later.